Imagine standing on a world where the sun never sets too harshly, where the oceans teem with possibilities we've never dreamed of, where the atmosphere cradles life with a tenderness Earth can only aspire to. Now imagine that this world isn't some fantasy, but a real place floating in the cosmic ocean, waiting. For decades, we've operated under a beautiful assumption, one that's woven into our very identity as a species. We've believed that Earth, our pale blue, represents the pinnacle of habitability in the universe. We've assumed that if life exists elsewhere, it must be struggling to match what we have here. But what if we've been wrong this entire time? What if Earth, for all its breathtaking beauty and life-sustaining magic, is actually just mediocre when it comes to hosting life? What if there are worlds out there, orbiting distant stars, that make our home look like a hostile desert by comparison? This isn't science fiction. This is the unsettling, exhilarating reality that astronomers and astrobiologists are confronting right now. There are at least 12 known exoplanets, worlds beyond our solar system, that scientists believe could be more habitable than Earth. Not equally habitable, more habitable. Let that sink in for a moment. Think about your own existence, about the delicate balance of conditions that allows you to breathe, to drink water, to feel the sun on your skin. Now consider that there might be places in the universe where all of this works better, where life doesn't have to struggle quite so hard, where evolution could have had an even better canvas to paint on. Before we venture into the depths of space to explore these alien worlds, ask yourself this question. If you could leave Earth tomorrow for a planet that offered better conditions for human survival, longer lifespans, more stable climates, and greater biodiversity, would you go? Would you abandon the only home our species has ever known for something objectively superior? Hold that question in your mind as we journey through this discovery, because by the end, you might find your answer has changed. The story begins not among the stars, but in the mind of a scientist who dared to question our cosmic significance. In 2014, a researcher named René Heller, working at McMaster University in Canada alongside his colleague John Armstrong, published a paper that would shake the astronomical community. The paper introduced a concept that seemed almost heretical: superhabitable planets. These weren't just planets that could support life like Earth does. These were worlds that, according to the metric scientists use to measure habitability, could support life better than Earth ever has or will. Heller and Armstrong didn't just speculate wildly. They carefully analyzed what makes Earth habitable and then asked a deceptively simple question. Could these conditions be optimized? To understand why some planets might be more habitable than Earth, you first need to understand what makes Earth habitable at all. Our planet sits in what astronomers call the Goldilocks zone, or the habitable zone, a region around our sun where temperatures are just right for liquid water to exist on a planet's surface. Not too hot that water boils away into space, not too cold that it freezes into permanent ice. Liquid water, as far as we know, is absolutely essential for life as we understand it. But the Goldilocks zone is just the beginning. Earth has a magnetic field that shields us from deadly solar radiation. It has plate tectonics that recycle nutrients and regulate the climate over geological timescales. It has a large moon that stabilizes its axial tilt, preventing wild climate swings. It has an atmosphere with just the right composition to trap heat without creating a runaway greenhouse effect. All of these factors, working in concert over billions of years, have made Earth a haven for life. But here's the thing that scientists like Heller realized: Earth's habitability is actually constrained by several factors. Our sun, for instance, is a G-type yellow dwarf star, and it has a lifespan of about 10 billion years. That sounds like a long time, and it is, but Earth will only remain in the habitable zone for about another billion years. After that, the sun will grow hotter as it ages, eventually boiling away our oceans and making complex life impossible long before it actually dies. Earth has already used up about half of its habitable lifetime. What if there were planets orbiting stars that live longer, giving life more time to evolve and diversify? What if there were planets slightly larger than Earth, with more surface area for diverse ecosystems and stronger gravity to hold onto thicker atmospheres? What if there were planets with more land masses and shallower oceans, providing more habitable terrain? What if there were planets with warmer average temperatures, allowing life to thrive across more of the surface without the dead zones of ice we see at Earth's poles? These weren't idle questions. Heller and Armstrong created a detailed list of characteristics that would make a planet superhabitable. The star should be a K-type orange dwarf, smaller and cooler than our Sun but longer-lived, potentially shining for 15 to 45 billion years. The planet should be about 10% larger than Earth and about 50% more massive, creating stronger gravity that helps retain a thicker atmosphere while still allowing for diverse life forms. The planet should be slightly warmer than Earth on average, perhaps by about 8 degrees Celsius, allowing for more biodiversity and fewer frozen wastelands. It should be older than Earth, but not too old, perhaps between 5 and 8 billion years old, giving life more time to become complex while ensuring the planet's internal heat engine hasn't completely died. The planet should have greater landmass distribution with archipelagos and shallow seas rather than deep oceans, maximizing habitable area. It should have a strong magnetic field and active plate tectonics, just like Earth, but optimized. When this paper was published, it sparked intense debate. Some scientists embraced the concept enthusiastically, recognizing that it opened new avenues for the search for extraterrestrial life. If we're looking for life beyond Earth, why should we only look for Earth-like planets when better options might exist? But others pushed back, arguing that we only have one example of a habitable planet to work from, so speculating about better versions is premature. There's truth to both perspectives, but what's undeniable is that the concept of superhabitability forced scientists to think more critically about what we're actually looking for when we search for alien life. Now, here's where the story takes a turn from theoretical to tangible. Since the launch of missions like Kepler, TESS, and the deployment of increasingly sophisticated ground-based telescopes, we've discovered over 5,000 confirmed exoplanets. Among these thousands of worlds, astronomers have identified specific candidates that match many, if not all, of the criteria for superhabitability. These aren't hypothetical planets in computer simulations. These are real worlds, orbiting real stars, and some of them are relatively close to us in cosmic terms. Let's journey to the first of these extraordinary worlds. Imagine you're standing on the surface of Kepler 442b, a planet that orbits a K-type orange dwarf star about 1,200 light-years from Earth in the constellation Lyra. Before you stands a sky tinted with hues unfamiliar to Earth-born eyes, the light from the orange sun casting everything in a perpetual golden hour glow. This planet is about 33% larger than Earth and orbits within its star's habitable zone, completing one orbit every 112 days. The star it orbits, Kepler 442, is smaller and cooler than our Sun, but here's the remarkable part. This star will shine for potentially 30 billion years or more. While Earth's window of habitability is closing, life on Kepler 442b, if it exists, has vast eons ahead of it still. The planet's larger size means stronger gravity, about 30% stronger than Earth's. If you were standing there, you'd weigh more, but that stronger gravity also means the planet can hold onto a thicker atmosphere more effectively. A thicker atmosphere provides better insulation against temperature swings, more protection from radiation, and potentially more stable weather patterns. Scientists have calculated that Kepler 442b receives about 70% of the light that Earth receives from the Sun. But because its atmosphere could be thicker and because its star is more stable, the surface temperature could be remarkably comfortable. Think about the implications of this. On Earth, we have extreme environments at the poles and scorching deserts at the equator. What if Kepler 442b has a more moderate climate across its entire surface? What if the difference between its coldest and warmest regions is far less dramatic than Earth's? This would mean more habitable land, more places where life could flourish without the extremes that challenge survival on our world. But Kepler 442b is just the beginning. Travel with me now across the interstellar void to another remarkable world, one that's even closer to us. Kepler 452b orbits a G-type star similar to our Sun, but older and slightly larger, about 1,400 light-years away in the constellation Cygnus. This planet, nicknamed Earth's cousin when it was discovered in 2015, is about 60% larger than Earth and orbits its star every 385 days, remarkably similar to Earth's year. What makes Kepler 452b potentially more habitable than Earth isn't necessarily any single factor, but the combination of its characteristics and, crucially, its age. The star it orbits is about 6 billion years old, 1.5 billion years older than our Sun. This means Kepler 452b has had 1.5 billion more years than Earth for life to potentially evolve. On Earth, life took about 3.5 billion years to progress from simple single-celled organisms to complex multicellular life. Imagine what an extra 1.5 billion years could accomplish. If life emerged on Kepler 452b at a similar time to when it emerged on Earth, it could be far more advanced, more diverse, more complex than anything we see in our biosphere. The larger size of Kepler 452b also matters tremendously. With 60% more surface area than Earth, there's simply more room for diverse ecosystems, more ecological niches for life to explore, more opportunities for evolution to experiment. Think about Earth's incredible biodiversity, from the depths of the Mariana Trench to the peak of Mount Everest, from Antarctic ice to Amazonian rainforests. Now imagine a world with 60% more surface area to distribute that diversity across. The mind reels at the possibilities. Ask yourself this question. If intelligent life did evolve on Kepler 452b, and if they looked out at the universe with telescopes as we do, would they consider Earth habitable, or would they see it as a barely adequate world, struggling to maintain its biosphere? Would they look at our ice caps and deserts and violent weather and think, that planet is trying its best, but it's clearly not optimal for life? Now we venture to a system that has captured the imagination of scientists and the public alike. TRAPPIST-1. This ultra-cool red dwarf star, about 40 light-years from Earth, hosts at least 7 Earth-sized planets, 3 of which orbit within the habitable zone. But it's TRAPPIST-1e that stands out as potentially super-habitable. This world is almost exactly Earth's size, receives about the same amount of light that Earth receives from the Sun, and likely has a substantial atmosphere. But here's what makes it special. Red dwarf stars like TRAPPIST-1 can shine for trillions of years. Not billions. Trillions. The universe is only about 13.8 billion years old. TRAPPIST-1 has barely begun its life. If life emerges on TRAPPIST-1e, it has an almost incomprehensible amount of time to evolve and flourish. Standing on TRAPPIST-1e would be an otherworldly experience in ways both familiar and alien. The star is so cool that it would appear deep red, bathing the landscape in crimson light. You might not be able to see it with your eyes the way you see our Sun, as much of its energy is emitted in infrared. But the planet likely receives enough energy for liquid water, possibly for vast oceans. Because TRAPPIST-1e is so close to its star, completing an orbit every 6 days, it's probably tidally locked, meaning one side of the planet always faces the star while the other side faces eternal night. But this doesn't necessarily mean the planet is uninhabitable. Atmospheric circulation could distribute heat from the day side to the night side, creating a potentially habitable twilight zone along the terminator, the boundary between day and night. Some scientists speculate that this twilight zone could be the most habitable region in the entire universe, with constant moderate temperatures, protected from the harsh radiation of direct starlight on the day side and the freezing cold of the night side. Imagine a belt around an entire planet where conditions are perpetually perfect, where the sun never rises too high or sets too low, where evolution could produce life forms adapted to this eternal dusk. The discovery of TRAPPIST-1 in 2017 sent ripples through the scientific community because it demonstrated that small, cool stars could host multiple potentially habitable planets. These stars are the most common type in our galaxy, making up about 75% of all stars. If red dwarf systems are capable of hosting habitable or even superhabitable planets, it means the universe could be teeming with worlds better than Earth. Let's continue our journey to another fascinating candidate, K2-18b. This planet, about 120 light-years away in the constellation Leo, made headlines in 2019 when scientists announced they had detected water vapor in its atmosphere, the first time this had been achieved for a planet orbiting in its star's habitable zone. K2-18b is what scientists call a mini-Neptune, about 8 times Earth's mass and over twice Earth's radius. It orbits a red dwarf star every 33 days. Now, you might think that a planet this massive would be a gas giant like Neptune or Uranus, but recent research suggests K2-18b might be a Hycean world, a type of planet covered by a global ocean with a hydrogen-rich atmosphere. Imagine an ocean world, a planet where the entire surface is covered by water hundreds of miles deep, potentially harboring life in those dark, pressurized depths. Earth's oceans, at their deepest, reach about 7 miles down. Imagine oceans hundreds of times deeper. What forms of life could exist in such an environment? On Earth, we've discovered entire ecosystems around hydrothermal vents on the ocean floor. Life that doesn't depend on sunlight but on chemical energy from the planet's interior. On a Hycean world like K2-18b, such ecosystems could be the norm rather than the exception. The discovery of water vapor and potentially other biosignatures like dimethyl sulfide, which on Earth is only produced by life, makes K2-18b one of the most tantalizing targets in the search for extraterrestrial life. But here's the question you should ask yourself. Would you consider a global ocean world more or less habitable than Earth? There would be no land, no terrestrial ecosystems, no forests or grasslands or mountains. But there would be unimaginable volumes of water, potentially more stable conditions than Earth's varied environments, and protection from cosmic radiation under miles of ocean. Is habitability about maximizing the diversity of environments, or is it about creating optimal conditions for life to thrive in whatever form it takes? Moving on, we encounter Kepler 1649c, a world that's almost exactly Earth-sized, orbiting in the habitable zone of a red dwarf star about 300 light-years away. What makes Kepler 1649c particularly interesting is how similar it is to Earth in terms of size and the amount of starlight it receives. It gets about 75% of the light Earth receives from the Sun, which could mean surface temperatures very similar to ours. But once again, the type of star makes all the difference. Red dwarf stars live far longer than our Sun, and they're also more stable in some ways. While they can produce powerful flares, once they settle into their main sequence life, they can maintain steady energy output for trillions of years. Kepler 1649c completes an orbit every 19.5 days and is likely tidally locked. But as we discussed with TRAPPIST-1e, this doesn't preclude habitability. In fact, some scientists argue that tidally locked planets might be more common among habitable worlds than planets with day-night cycles like Earth. Think about the evolutionary pressures on a tidally locked world. Life on the day side would need to cope with constant, intense starlight and heat. Life on the night side would need to survive in perpetual darkness and cold. But life in the twilight zone would experience the kind of environmental stability that's rare on Earth, where day and night, seasons, and climate variations create constant change. Stability can be a double-edged sword. Too much change and life struggles to adapt. Too little change and evolution slows. But moderate, consistent conditions might allow life to become incredibly efficient, perfectly adapted to its environment in ways that Earth life, constantly battling changing conditions, never could achieve. Our next destination takes us to a star system that's practically in our cosmic backyard, Proxima Centauri b. Orbiting Proxima Centauri, the closest star to our Sun at just over 4 light-years away, this planet has been the subject of intense study since its discovery in 2016. Proxima b is at least 1.3 times Earth's mass and orbits within the habitable zone of its star, completing an orbit every 11 days. The proximity of this planet to Earth makes it one of the most important targets for future observation and, speculatively, even future exploration. If humanity ever develops the technology to send probes or even missions to other star systems, Proxima Centauri b would be the first stop. But Proxima b faces challenges. Proxima Centauri is a red dwarf known for powerful stellar flares, bursts of radiation that could strip away a planet's atmosphere and bombard the surface with harmful radiation. However, if Proxima b has a strong magnetic field like Earth does, it could deflect much of this radiation. And some scientists have theorized that planets around active stars might develop thicker atmospheres and stronger magnetic fields as an evolutionary response to the harsh radiation environment. In this scenario, Proxima b wouldn't just be habitable despite its star's flares. It might be superhabitable because of them, having developed robust protective mechanisms that make it even more resilient than Earth. Imagine standing on Proxima b, looking up at the sky to see not only the red glow of Proxima Centauri but also, clearly visible, the binary system of Alpha Centauri A and B, two sun-like stars appearing as the brightest objects in the night sky. And if you looked carefully, you might even spot our Sun, a pale yellow star among many others, the point of origin of any humans who might one day visit this world. Let's turn our attention now to a planetary system that challenges our understanding of habitability. LHS 1140b. This super-Earth, about 1.7 times Earth's radius and nearly 7 times Earth's mass, orbits a red dwarf star about 40 light-years away. Discovered in 2017, LHS 1140b quickly became a top candidate for habitability studies. The planet orbits every 25 days and sits comfortably within its star's habitable zone. What makes LHS 1140b particularly promising is its density, which suggests it's a rocky world rather than a mini Neptune. Recent observations have suggested that LHS 1140b might be covered by a global ocean or might have a large ocean covering part of its surface. The planet star is relatively quiet for a red dwarf, producing fewer of the dangerous flares that plague planets in systems like Proxima Centauri. The higher gravity on LHS 1140b, nearly 3 times that of Earth, would create a drastically different environment than we're used to. You would weigh 3 times as much, movement would be more difficult, and any life forms that evolved there would likely be built low to the ground, sturdy and robust rather than tall and slender. But that stronger gravity also means the planet can hold onto a much thicker atmosphere, providing better insulation, more protection from radiation, and potentially more stable weather patterns. A thicker atmosphere also means higher atmospheric pressure at the surface, which allows liquid water to exist at higher temperatures. On Earth, water boils at 100 degrees Celsius at sea level, but on a planet with higher atmospheric pressure, water could remain liquid at much higher temperatures, potentially expanding the range of habitable environments. Picture an ocean world where the seas are significantly warmer than Earth's tropical oceans, teeming with life that has adapted to these higher temperatures and pressures. On Earth, extremophile organisms thrive in conditions we once thought impossible for life. In boiling hot springs, in acidic lakes, in the crushing pressure of the deep ocean. What if on LHS 1140b, these extreme conditions are the norm, and life has had billions of years to adapt and flourish in them? Now we come to Kepler 62f, a super-Earth about 40% larger than our planet, orbiting in the habitable zone of a K-type orange dwarf star about 1,200 light-years away. Kepler 62f orbits its star every 267 days, and its size and orbital position suggest it could have surface conditions remarkably similar to Earth. But what sets Kepler 62f apart is the stellar environment. K-type stars, as we've mentioned, are considered by many scientists to be the optimal type of star for hosting habitable planets. They're cooler and smaller than our Sun, so their habitable zones are closer in, but they live much longer, giving life more time to evolve. They're also more stable than red dwarfs, producing fewer dangerous flares while still maintaining steady energy output for tens of billions of years. Kepler 62f is part of a 5-planet system, meaning any life that evolved there would look up at a sky potentially featuring multiple planets visible to the naked eye. A solar system bustling with worlds in a way ours is not when viewed from Earth's surface. Scientists have run climate models for Kepler 62f, testing different atmospheric compositions and finding that with the right amount of carbon dioxide, the planet could maintain liquid water on its surface and potentially support life. Some models suggest Kepler 62f could be entirely covered by ocean, while others suggest it might have continents and islands. We won't know for certain until we develop more advanced observational techniques. But the fact that multiple models show habitability is encouraging. Consider this question. If Kepler-62f is an ocean world, and if life exists there, would it necessarily follow the same evolutionary path as life on Earth? On Earth, life began in the oceans and eventually colonized land, leading to the incredible diversity of terrestrial life we see today. But if a planet has no land, would life ever develop the structures and capabilities we associate with complexity, or would it take entirely different paths we can't even imagine? Our journey takes us next to Kepler-186f, a planet with a special significance in the history of exoplanet discovery. When it was announced in 2014, Kepler-186f was the first Earth-sized planet discovered in the habitable zone of another star. It's about 10% larger than Earth and orbits a red dwarf star about 580 light-years away, completing one orbit every 130 days. Kepler-186f is part of a 5-planet system, but it's the outermost planet and the only one in the habitable zone. The planet receives about 1/3 the light that Earth receives from the Sun, which means it's likely cooler than Earth. However, with the right atmospheric composition, particularly a greenhouse effect from gases like carbon dioxide, the planet could maintain liquid water on its surface. Imagine a world perpetually locked in conditions similar to Earth's Arctic or Antarctic regions during their mild seasons. Not frozen wastelands, but cool, crisp environments where life is adapted to lower temperatures and dimmer light. On Earth, we see incredible resilience in life at high latitudes, organisms that have found ways to thrive in cold, dark conditions. On Kepler-186f, such adaptations might be universal, creating a biosphere of cold-adapted life forms that would find Earth's tropical regions unbearably hot. The discovery of Kepler-186f was emotionally significant for many people because it was the first concrete proof that planets very similar to Earth in size exist in the habitable zones of other stars. Before Kepler-186f, we had found many exoplanets, but they were mostly gas giants or planets in hostile environments. Kepler-186f showed us that worlds like ours are out there, waiting to be found. Next, we travel to a system that contains not one but possibly 2 superhabitable candidates, Kepler-296e and Kepler-296f. These planets orbit a red dwarf star about 1,700 light-years away. Both are larger than Earth but smaller than Neptune, placing them in the category of super-Earths or mini-Neptunes. Kepler-296e orbits every 34 days and receives about 43% of the light Earth receives, while Kepler-296f orbits every 63 days and receives about 25% of Earth's light. The system star is about half the size of our Sun and much cooler, meaning these planets, despite their close orbits, could have temperate conditions. What's fascinating about this system is that we have 2 candidates for habitability so close together. On Earth, we often think about the Moon and how its presence has stabilized our planet's tilt and affected our oceans through tides. Imagine living on a planet where another potentially habitable world is visible in the sky, a constant reminder that you're not alone in your cosmic neighborhood. If life evolved on both Kepler-296e and Kepler-296f, they would be able to see each other clearly, 2 habitable worlds in the same system. The philosophical implications are staggering. Would 2 intelligent species evolve in the same system, always aware of each other's existence? Would they eventually find ways to communicate, to visit each other? Or would they remain forever separate, 2 isolated branches of life gazing across the cosmic gulf at each other? We must also discuss Kepler-283c, a planet about 1.8 times Earth's radius orbiting a red dwarf star about 1,700 light-years away. Kepler-283c orbits every 93 days and sits squarely in the middle of its star's habitable zone, receiving about 60% of the light Earth receives. Its larger size suggests it could be a super-Earth with a thick atmosphere, strong gravity, and potentially a very active geological cycle. One of the criteria for superhabitability is active plate tectonics, which on Earth has been crucial for regulating the climate, recycling nutrients, and creating diverse habitats through mountain building and ocean floor spreading. A larger planet like Kepler 283c might have even more vigorous plate tectonics than Earth, leading to a more dynamic surface with faster nutrient cycling and greater geological diversity. Think about Earth's most biodiverse regions: tropical rainforests, coral reefs, coastal zones where land and sea meet. These are areas where nutrients are abundant and constantly recycled, where energy from the sun is plentiful, and where the physical environment creates countless niches for life to exploit. On a planet with more active geology and more surface area, these productive zones could be even more extensive and more diverse. The Amazon rainforest, one of the most biodiverse places on Earth, might look sparse compared to what could exist on a true superhabitable world. Let's turn our attention to TOI 700d, a planet discovered by NASA's TESS mission and announced in 2020. This Earth-sized world orbits in the habitable zone of a red dwarf star about 100 light-years away, completing one orbit every 37 days. 700d is about 20% larger than Earth and receives about 86% of the energy that Earth receives from the Sun. What makes TOI 700d particularly exciting is its proximity to us in cosmic terms, and the fact that it was discovered by TESS, a mission specifically designed to find nearby exoplanets suitable for follow-up study. TOI 700d is close enough that future telescopes, like the James Webb Space Telescope, can analyze its atmosphere and search for signs of life. Imagine the moment when we point our most powerful telescope at a planet like TOI 700d and detect oxygen and methane in its atmosphere, the kind of chemical disequilibrium that on Earth is maintained by life. Or imagine detecting industrial pollutants, the unmistakable signature of a technological civilization. How would humanity react to the confirmation that we are not alone? Would it unite us in wonder and curiosity, or would it divide us in fear and disagreement about what to do next? Our final candidate brings us to GJ667cc, a super-Earth at least 4.5 times Earth's mass orbiting in the habitable zone of a red dwarf star about 22 light-years away. GJ667cc orbits its star every 28 days and receives about 90% of the light Earth receives. But because much of that light is in infrared, the actual surface temperature could be quite different from what we'd expect. The star, GJ667c, is part of a triple star system, meaning that if you stood on GJ667cc and looked up, you would see not one sun but potentially three, though two would appear very distant. The primary star would cast the planet in red light, while the other two stars would appear as bright points in the sky, perhaps as bright as the full moon appears from Earth. GJ667cc challenges our assumptions about what kinds of stellar environments can host habitable planets. We once thought that multi-star systems would be too chaotic, with gravitational perturbations preventing stable planetary orbits. But GJ667cc demonstrates that planets can exist in complex gravitational environments and still maintain stable, potentially habitable conditions. The planet's higher mass means stronger gravity and likely a thicker atmosphere, fitting the profile of a superhabitable world. Now, having journeyed through these 12 remarkable worlds, we must address the larger implications of their existence. The discovery of potentially superhabitable exoplanets forces us to reconsider our place in the universe in profound ways. For all of human history, Earth has been all we've known. Every philosopher, every scientist, every artist, every ordinary person who has ever lived has done so on this one planet. Our entire conception of life, of habitability, of what's possible in the universe, has been shaped by this single example. We've built our civilization on the assumption that Earth is special, that it represents something exceptional in the cosmos. And in many ways, it is special. The precise combination of factors that led to Earth's habitability and to the evolution of intelligent life is unique. But unique doesn't mean optimal. The concept of superhabitability isn't just about finding other places where life might exist. It's about expanding our understanding of what life needs to thrive. When we search for extraterrestrial life, we've typically looked for planets that are as similar to Earth as possible. But what if this approach has been too narrow? What if life is more common on superhabitable planets than on Earth-like planets? What if the universe is teeming with life, but it's thriving on worlds we haven't been paying enough attention to because they don't look exactly like home? Consider the time scales involved. Earth is about 4.5 billion years old. Life appeared relatively quickly in Earth's history, within the first billion years or so, but it took another 3 billion years for complex multicellular life to evolve. Intelligent life capable of technology has only existed for a tiny fraction of Earth's history, maybe 200,000 years if we're being generous, and technological civilization as we know it has existed for only about 200 years. Now think about a planet like Kepler 442b or TRAPPIST-1e, orbiting stars that will shine for tens of billions or even trillions of years. If life appeared on those planets on a similar timescale to Earth, it could be billions of years more advanced than life on Earth. Not just more advanced technologically, though that's mind-boggling enough, but more advanced evolutionarily, ecologically, in ways we might not even have concepts for. What would a biosphere look like after 10 billion years of evolution? On Earth, we've seen life progress from single-celled organisms to the incredible diversity we see today in 4 billion years. Double that time, triple it, or multiply it by 100. Would ecosystems become more complex, more efficient, more resilient? Would intelligence be common or rare? Would technological civilizations inevitably destroy themselves, or would they find ways to live in harmony with their planets for geological timescales? These are questions we can barely begin to answer, but the existence of planets older than Earth, planets with more time for life to develop, means these questions aren't just philosophical. They're real possibilities playing out on real worlds. There's another implication that's both exciting and sobering. If superhabitable planets exist, and if they're relatively common, then the search for extraterrestrial intelligence should perhaps focus on these worlds rather than Earth-like planets. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. One of the factors in the equation is the fraction of planets that could support life where life actually appears. Another is the fraction of those planets where intelligent life evolves. If superhabitable planets provide better conditions for life to emerge and evolve, then both of these fractions might be higher for superhabitable planets than for Earth-like ones. This means that when we listen for signals from alien civilizations, we might have better luck if we point our antennas at K-type and M-type stars rather than Sun-like G-type stars. But there's a darker possibility to consider. If Earth is merely mediocre in terms of habitability, what does that mean for our long-term survival as a species? We've already stressed our planet systems in profound ways. Climate change, biodiversity loss, pollution, resource depletion. These are all signs that we're pushing Earth beyond its capacity to maintain the stable conditions that allowed our civilization to flourish. If we lived on a superhabitable planet with thicker atmospheres, more stable climates, greater biodiversity, and more robust ecological systems, would we be able to damage it as thoroughly as we've damaged Earth? Or is Earth's relative fragility one of the things that makes our current situation so precarious? This raises an ethical question that humanity will eventually have to confront. If we develop the technology to travel to other star systems, and if we find that some of these superhabitable planets are indeed better suited to life than Earth, do we have a right to settle them? If they're uninhabited, the question might seem straightforward, though even then we'd have to grapple with whether we have the right to introduce Earth life to alien ecosystems. But what if we find that these superhabitable planets are already teeming with life? Perhaps even intelligent life. Do we have any claim to them? Or should they remain the domain of whatever life already exists there? And if we find intelligent civilizations on superhabitable planets, civilizations that have had billions of years more than us to develop, what would we even say to them? What could we possibly offer being so far advanced beyond us? These questions might seem like science fiction, but they're becoming increasingly relevant as our technology advances. The James Webb Space Telescope, launched in 2021, has already begun analyzing the atmospheres of exoplanets, searching for chemical signatures that might indicate life. Future missions like the Habitable Exoplanet Observatory, proposed by NASA, could directly image exoplanets and analyze their atmospheres in even greater detail. Within your lifetime, we might detect definitive signs of life on another planet. Within your children's lifetime, we might be able to characterize that life, to understand what kind of organisms produce the biosignatures we detect. And within a few more generations, we might develop the technology to actually visit these worlds. The discovery of potentially superhabitable exoplanets also changes how we think about planetary protection and conservation. On Earth, we've learned hard lessons about the fragility of ecosystems and the unintended consequences of human activity. We've driven countless species to extinction, altered the chemistry of the atmosphere and oceans, and changed the face of the planet in ways that will be visible in the geological record for millions of years. We call our current era the Anthropocene, the age of humans, defined by our impact on the planet. If we ever gain access to other habitable or superhabitable planets, we'll carry the lessons of Earth with us. Will we repeat the same mistakes on a grander scale, or will we have learned to live more sustainably? There's also a profound psychological dimension to the discovery of superhabitable planets. Human exceptionalism has taken many forms throughout history. We once believed Earth was the center of the universe, with everything revolving around us. Copernicus showed us that Earth orbits the Sun, not the other way around. We once believed our solar system was unique, but we now know of thousands of other planetary systems. We once believed that life was something special to Earth, a unique cosmic accident, but the discovery of the chemical building blocks of life in meteorites and in interstellar space has shown us that the ingredients for life are common. And now we're learning that Earth itself might not even be the best kind of planet for life. Each of these discoveries has forced us to revise our understanding of our place in the cosmos, to become a little less arrogant and a little more humble. But there's also something empowering about these discoveries. Knowing that there are potentially better worlds out there doesn't diminish Earth's beauty or the preciousness of the life that has evolved here. If anything, it should make us appreciate what we have more deeply. Earth might not be the most habitable planet in the universe, but it's our home. Every ecosystem, every species, every human culture has been shaped by the specific conditions of this world. We are Earth life, adapted to Earth's gravity, Earth's atmosphere, Earth's day-night cycle, Earth's seasons. Even if we found a superhabitable planet and somehow transported ourselves there, we would be aliens, our bodies and minds shaped by a different world. This brings us to another question you should ask yourself. What does habitable really mean? Scientists define habitability primarily in terms of the capacity to support liquid water and, by extension, life as we know it. But habitability for microbial life might be very different from habitability for complex multicellular life, which might be very different from habitability for intelligent life, which might be very different from habitability for human life specifically. A planet might be superhabitable for microbes, with vast areas of liquid water and abundant chemical energy sources, but it might have such high gravity or such a different atmospheric composition that humans could never survive there without extensive technological support. Conversely, a planet might be perfect for humans in terms of gravity, atmosphere, and temperature, but it might lack the geological or chemical conditions that would allow a native biosphere to develop. The 12 planets we've discussed represent our current best candidates for superhabitability based on the data we have, but this list is far from definitive. Our techniques for studying exoplanets are still in their infancy. We can measure a planet's size, mass, and orbit fairly accurately, but determining whether it has an atmosphere, what that atmosphere is made of, whether it has liquid water on its surface, whether it has a magnetic field, whether it has plate tectonics, all of these require much more sophisticated observations than we're currently capable of for most exoplanets. The planets on our list are candidates based on models and estimates, but until we develop better observational techniques, we can't be certain of their true conditions. This uncertainty is part of what makes the search for superhabitable planets so exciting. We're at the very beginning of this journey. The first exoplanet orbiting a sun-like star was only discovered in 1995, less than 30 years ago. In that short time, We've gone from knowing of 0 planets outside our solar system to knowing of over 5,000. Our technology is improving exponentially. Telescopes that seemed impossible a generation ago are now operational. Analysis techniques that would have taken years can now be done in days or hours. And we're only getting better at this. Every year brings new discoveries, new techniques, new insights. Within the next few decades, we'll likely have a much clearer picture of which exoplanets are truly habitable or superhabitable. We'll be able to map their continents and oceans if they have them. We'll be able to detect seasonal changes in their atmospheres. We'll be able to search for biosignatures with a level of precision that will tell us not just life might exist here, but life almost certainly exists here, and it's producing these specific compounds. And perhaps, if we're very lucky and very persistent, we'll detect technosignatures, the unmistakable signs of technology, industrial pollutants, radio transmissions, perhaps even artificial structures large enough to be visible from interstellar distances. The search for superhabitable planets also intersects with one of the most profound questions in science and philosophy. Are we alone? The Fermi paradox, named after physicist Enrico Fermi, asks why, if the universe is so vast and so old, we haven't detected any signs of extraterrestrial civilizations. There are many proposed solutions to this paradox. Maybe intelligent life is extremely rare. Maybe civilizations inevitably destroy themselves before they can spread beyond their home planets. Maybe the distances between stars are simply too vast for communication or travel to be practical. Maybe we're looking in the wrong places or in the wrong ways. Or maybe, and this is a chilling thought, there's something out there that prevents civilizations from making themselves known, some danger we haven't yet encountered. The existence of superhabitable planets adds another dimension to the Fermi paradox. If life is more likely to emerge and thrive on superhabitable planets than on Earth-like planets, and if intelligent life follows the same pattern, then maybe we've been looking in the wrong places. Most of our SETI efforts have focused on sun-like stars because that's what we know. But if the most advanced civilizations in the galaxy evolved on planets orbiting K-type or M-type stars, we might have been missing them entirely. It's also possible that civilizations on superhabitable planets, living in more stable and abundant conditions than we do on Earth, might have less incentive to develop space travel or to send out signals. If your planet provides everything you need and will continue to do so for billions of years, why take the risk and expense of venturing into the hostile environment of space? Or perhaps the opposite is true. Perhaps civilizations on superhabitable planets, freed from the constant struggle for survival that has characterized much of Earth's history, have more time and resources to devote to science, exploration, and philosophy. Perhaps they've achieved post-scarcity societies where everyone has their basic needs met, allowing them to focus on understanding the universe and seeking out other life. Perhaps they've been exploring the galaxy for millions or billions of years, and they already know about us. Perhaps they're watching, waiting for us to mature as a species before making contact. Or perhaps they visited Earth long ago and found it too harsh, too unstable, too marginally habitable to be of interest. These are speculations, of course, ventures into the realm of what-ifs and maybes. But they're speculations grounded in real science, in the real discovery that planets potentially more habitable than Earth actually exist. The fact that we can now point to specific stars and say, there, orbiting that star, is a world that might be better suited to life than Earth, is extraordinary. It's a testament to human ingenuity and curiosity that we've come this far in such a short time. Let's ground ourselves back in the science for a moment and discuss what we still need to learn. The concept of superhabitability is based on models of how planetary systems work, how life emerges and evolves, and what conditions are optimal for these processes. But we only have one example of a planet with life to study: Earth. This is a fundamental limitation in astrobiology. We can make educated guesses about what makes a planet habitable based on what we know about Earth life, but until we actually find life on another planet, we can't be certain our models are correct. It's entirely possible that life is far more adaptable than we think and can thrive in conditions we consider hostile. It's also possible that life is far more fragile than we think and requires specific conditions we haven't even identified yet. One of the key unknowns is the role of a planet's moon or moons. Earth's moon has played a crucial role in our planet's habitability. It stabilizes Earth's axial tilt, preventing wild climate swings. It creates tides that mix the oceans and create dynamic coastal environments. Some scientists think the moon was crucial for the emergence of life on Earth, while others think it's helpful but not essential. We don't yet have the ability to detect moons around exoplanets, though this is an area of active research. It's possible that some of the super-habitable candidates we've discussed have large moons that make them even more habitable, or it's possible that some lack moons entirely and are therefore less habitable than our models suggest. Another key unknown is the presence and strength of magnetic fields. Earth's magnetic field, generated by the movement of molten iron in our planet's core, shields us from harmful solar radiation and prevents our atmosphere from being stripped away by the solar wind. Mars, which lacks a strong global magnetic field, lost most of its atmosphere billions of years ago, transforming from a potentially habitable world into the cold, dry desert we see today. For a planet to be truly superhabitable, it almost certainly needs a strong, long-lasting magnetic field. Larger planets, like many of the super-Earths we've discussed, should in theory have more vigorous internal dynamics and therefore stronger magnetic fields. But we can't yet measure the magnetic fields of exoplanets directly. The composition of a planet's atmosphere is another crucial factor we're only beginning to be able to study. The James Webb Space Telescope has made headlines with its ability to analyze the atmospheres of some exoplanets, but we're still limited to the largest planets and those that transit their stars, passing between the star and Earth from our perspective, which allows starlight to filter through the atmosphere and reveal its composition. For most of the planets on our superhabitable list, we don't yet have detailed atmospheric data. We can estimate what their atmospheres might be like based on the planet's size, mass, and distance from its star, but these are educated guesses, not direct measurements. We also need to consider the role of a planet's geology in maintaining habitability over long time scales. Earth's plate tectonics, the process by which the planet's crust is constantly recycling, has been crucial for regulating our climate. Carbon dioxide is removed from the atmosphere through weathering of rocks and is then subducted into the mantle at tectonic plate boundaries. Volcanic activity releases carbon dioxide back into the atmosphere. This carbon cycle has kept Earth's climate relatively stable over billions of years despite the sun's increasing brightness. Planets without plate tectonics might not have this stabilizing mechanism, leading to runaway greenhouse effects or icehouse climates over geological timescales. Some of the planets on our list might be too small to maintain plate tectonics for billions of years, while others might have plate tectonics that are too vigorous, leading to constant volcanic catastrophes. Yet another factor is the planet's location within the galaxy. Our solar system is located in what some scientists call the galactic habitable zone, a region of the Milky Way that's not too close to the galactic center, where radiation and gravitational disturbances are common, and not too far out in the galactic hinterlands, where heavy elements necessary for planet formation are rare. All of the superhabitable candidates we've discussed are relatively nearby in cosmic terms, within a few thousand light-years, so they're all in roughly the same galactic neighborhood as us. But if we expanded our search to the entire galaxy, we might find that the most habitable regions are different from where we happen to live. Now, let's consider a thought experiment that brings all of this into sharp focus. Imagine that tomorrow, scientists announce definitive proof that one of these 12 planets, let's say Kepler 442b, has a breathable atmosphere, liquid water oceans covering 70% of its surface, continents with lush vegetation, and clear biosignatures indicating a thriving biosphere. Not only that, but the planet is definitively more stable, more hospitable, and more conducive to life than Earth. The announcement sends shockwaves around the world. Humanity now knows for certain that we are not alone and that there's a better world out there. What happens next? The political implications would be staggering. Every nation with a space program would immediately begin planning missions to study Kepler 442b more closely. International cooperation would compete with national pride and the desire to be the first to make contact or claim territory. Corporations would see opportunities for resources and expansion. Philosophers and ethicists would debate our moral obligations to any life already on the planet. Religious leaders would grapple with the theological implications. And ordinary people would have to reckon with the knowledge that Earth, our cherished home, is not the pinnacle of habitability we'd assumed. There would likely be a movement to protect Kepler 442b from human interference, a planetary protection protocol on a scale we've never attempted. After all, if the planet has its own biosphere, introducing Earth life could be catastrophic, leading to biological contamination or even the extinction of native life forms. We've seen on Earth how invasive species can devastate ecosystems. Imagine the damage we could do on an interstellar scale. But there would also be those who argue that if Kepler 442b is more habitable than Earth, we have a duty to ensure the survival of Earth life by establishing a presence there, especially if Earth becomes uninhabitable due to climate change or other catastrophes. This thought experiment isn't as far-fetched as it might seem. We're approaching the technological capability to detect biosignatures on exoplanets. The James Webb Space Telescope is already searching. Future missions will be even more capable. Within a few decades, we might have the answer to whether life exists on one or more of these superhabitable candidates. And then humanity will have to decide what to do with that knowledge. But let's bring this back to you, personally. Why should you care about planets light years away that you'll almost certainly never visit? What difference does it make to your daily life whether Kepler 442b or TRAPPIST-1e are more habitable than Earth? The answer goes beyond the practical and into the realm of meaning and perspective. Knowing that there are potentially better worlds out there changes how we think about our place in the universe. It makes our problems seem both more urgent and more manageable. More urgent because Earth's habitability isn't guaranteed and isn't exceptional. We could lose what we have. More manageable because the universe is vast and full of possibilities, and our story doesn't have to end on this one planet. The search for superhabitable planets also drives technological innovation in ways that benefit us here and now. The same technologies we develop to study exoplanets also help us study Earth's climate and ecosystems. The modeling techniques we use to predict conditions on distant worlds help us predict our own planet's future. The international cooperation required for major space missions can serve as a model for cooperation on Earth. And the sense of wonder and curiosity that drives the search for other worlds inspires new generations of scientists, engineers, and explorers who will solve the challenges we face. There's also something deeply moving about the search for superhabitable planets. It represents humanity at its best. Curious, ambitious, humble enough to question our assumptions, and brave enough to seek out truths that might challenge our worldview. Every time we point a telescope at a distant star and discover a new planet, we're pushing back the boundaries of the known. We're venturing into territory that no human has explored before. We're asking questions that no previous generation had the tools to answer. And we're doing it not for immediate profit or survival, but because we're driven to understand, to explore, to know. As we near the end of this journey through space and possibility, it's worth reflecting on what we've learned. We've traveled to 12 worlds, each unique, each potentially offering conditions for life that equal or exceed Earth's. We've stood on the twilight zones of tidally locked planets, gazed at the crimson light of red dwarf stars, imagined oceans hundreds of miles deep and biospheres billions of years old. We've confronted the humbling possibility that Earth, for all its beauty, might be just mediocre in the grand scheme of habitability. And we've grappled with questions that have no easy answers. What is our responsibility to other worlds? How should we search for life? What would contact with an alien civilization mean for humanity? These 12 planets, Kepler 442b, Kepler 452b, TRAPPIST-1e, K2-18b, Kepler 1649c, Proxima Centauri b, LHS 1140b, Kepler 62f, Kepler 186f, Kepler 296e and F, Kepler 283c, TOI 700d, and GJ 667cc, are more than just catalog entries or points of light in the night sky. They're real places, as real as Earth, with their own histories stretching back billions of years. They might host ecosystems we can't imagine, life forms adapted to conditions we find alien, perhaps even civilizations that have been exploring the cosmos since before Earth had multicellular life. Or they might be barren rocks, their potential for habitability unrealized, waiting for life to emerge or to be brought from elsewhere. We stand at a unique moment in human history. For the first time, we have the technology to not just speculate about other worlds, but to actually study them, to gather data about their composition, their atmospheres, their potential for life. Future generations will look back at this era as the time when humanity first reached out beyond our solar system and began to truly explore the galaxy. They'll study the discoveries we're making now the way we study the voyages of ancient explorers who mapped Earth's continents and oceans. And they might wonder why it took us so long to realize that Earth, while precious and unique to us, is just one world among countless others, and possibly not even the best one for life. The search continues. Every night, telescopes around the world and in space are gathering light from distant stars, looking for the telltale dimming that indicates a planet passing in front of its star. Supercomputers are analyzing this data, searching for patterns, identifying candidates for further study. Scientists are refining their models, predicting which planets are most likely to be habitable or superhabitable. Engineers are designing the next generation of telescopes and spacecraft that will give us even clearer views of these distant worlds. And somewhere, perhaps on one of the 12 planets we've discussed, perhaps on a world we haven't even discovered yet, life might be looking back at us, wondering the same questions we're wondering. Are we alone? What else is out there? Is our world the best that's possible, or is there something better? We don't yet have all the answers, and we may not have them for decades or even centuries. But we're asking the questions, and we're developing the tools to answer them. That's what makes this such an exciting time to be alive. You are living through the early stages of humanity's expansion into the cosmos, the era when we first confirmed that planets exist around other stars and began to characterize them, to understand them, to dream about them. Future generations might take interstellar travel for granted, might think nothing of the idea that there are countless habitable worlds scattered throughout the galaxy. But you get to experience the wonder of discovery, the first glimpses of what's out there. So the next time you look up at the night sky, remember that many of those points of light are more than just stars. They're suns with their own families of planets. Some of those planets might be barren and lifeless. Some might host simple life forms, microbes clinging to existence in harsh environments. And some, just maybe, might be superhabitable worlds where life has flourished for billions of years, creating ecosystems of breathtaking complexity and beauty. You're looking at a galaxy full of possibilities, a universe where Earth, for all its wonder, might be merely average. That thought should fill you with both humility and hope. Humility because it reminds us that we're not the center of the universe, that our planet and our species are part of a much larger story. Hope because it shows us that the universe is full of potential, full of places where life might thrive, full of opportunities for discovery and exploration that will challenge and inspire humanity for generations to come. The search for superhabitable planets isn't just about finding better real estate in the cosmic neighborhood. It's about understanding our place in the universe, about pushing the boundaries of knowledge, about ensuring that life, whether Earth-based or alien, has a future among the stars. And so the question remains, hanging in the air like the stars themselves. If we found a world truly better than Earth, a paradise among the planets, what would we do? Would we protect it, study it from afar with reverence and care? Would we attempt to reach it, to see it with our own eyes, to walk on its surface and breathe its air? Would we change our own world for the better, inspired by the knowledge of what's possible? There's no single answer, and perhaps that's appropriate. The universe is vast enough to contain all possibilities, and humanity's future among the stars has yet to be written. But one thing is certain, We're no longer limited to wondering if habitable worlds exist beyond Earth. We know they do. We've found them. And among them, hiding in the cosmic vastness, might be places that make Earth look like a rough draft, a first attempt at habitability that the universe later perfected elsewhere. That possibility, thrilling and humbling in equal measure, is what drives us forward into the dark, searching, always searching, for what lies beyond.